I don't write a whole lot about what I count on points for, because I try to get them out as quickly as possible. So if you have any questions about why you missed some points, just let me know. I'll tell you. Let's see. Last time we did watch that video, right? The home video thing where they lost all their stuff and then they were playing basketball afterwards. I want to show you. One option you have actually for honors credit. If you're an honors student, then you can get honors credit in this class. I think the due date is already passed with that, but if you want to get honors credit, just go see Dr. Tuesday. He's a pushover. He'll let you extend the date, right? Who's honors? My honors student. He'll let you extend the date probably. If you ask him really nicely, I'm sure that he would. But one of the options that you have is that you can attend some sporting event. It doesn't have to be, like a varsity sporting event. It can be one of these Greek events or whatever, but like it could be a volleyball game at 1 o'clock on Saturday. I think they're playing Southern or somebody, I forget. But anyway, you can go to the sporting event and record the video of the event and then analyze the motion of either the players or the balls or whatever it is that's in that event. And so we'll do that here. This is with Logger Pro. We use this in lab, but it's pretty simple to use once you get the hang of it. I'm just going to set my origin there, set my scale. How tall is that guy, you think? Roughly in meters, he's about 2 meters. He's 6 foot or maybe even a little more. And so we'll set our scale to be the height of that guy. And now I'm going to click on my basketball as it moves through its trajectory. Now initially, its velocity in the y direction is big, and then as it gets closer to the top, it's going to slow down. So you'll see that the dots will get closer and closer. As it slows down, you can see it's starting to slow down there at the top, and now it's turning over. It's going to start coming back down again, and I'll stop just before it gets to the hoop. And then we'll look at the plots. I just want to point out a couple of things to you about that. Okay, so first of all, if I just show the x position, and you have a plot of this in your book, but if I just show the x position, what can you think about the slope of this graph? It has a positive slope, and is the slope increasing, decreasing, or staying the same? Staying the same. So that means the acceleration of this object is 0, right? So since the velocity here is not changing, that means the slope is not changing, so the acceleration is 0. It has a constant positive slope. See, that slope is about almost 5 meters per second. So in the x direction, this ball is traveling at about 5 meters per second. Now notice if we look at the y position, this is the y position. Notice that the slope begins big and positive, and then it gradually gets smaller and smaller until at the top the slope is equal to 0. So this is just like our free fall problems that we had before, where if I throw something up in the air, it goes up and then it stops and then it comes back down again. So this is at the top of the trajectory where the speed of the object goes to 0. And then it begins to come back down again, increasing in the negative direction. Go back to our acceleration. If the slope is positive and decreasing, that means the acceleration has what sign? Positive, negative, or 0? It has a negative sign. If the slope is positive and decreasing, that means the slope is opposite, the acceleration is opposite the sign of the slope or negative. Over here it's negative and increasing in speed. That also means the acceleration is negative. If we look at the v versus t graph, I'm going to look at the y velocity here. Notice it does have a negative slope, and the negative slope is a indication of the acceleration of this graph. Okay? You will have some more qualitative type things on this next exam when we look at projectile motion. So make sure that you're still up on that. Also notice here that the y velocity goes to 0. This is at what point of the trajectory? At the very top of it. All right. That's a nice simple thing. If you want to do that for honors credit, you can, I think I attend think I said attend 3 to 4 sporting events on campus, record them, and I can help you if you don't know how to do this, which you might not. You can bring those videos to me, and I can help you and give you some guidance. Okay, so just on here, just to recap, I have a positive slope here. I have slope equals 0 here, and then a negative slope. Because of what the slope is doing, this tells me that I have a negative acceleration looking at the y displacement. Also looking at the x displacement, this is a constant slope. That means that the acceleration is equal to 0, or Vx is constant. And then if we look at the velocity graph, this is the Vy versus t. The slope of this equals the acceleration in the y direction, which is equal to negative 10 meters per second squared. And then the slope of this, I didn't show you this, but this is the x velocity, and it has a 0 slope. So that tells us, as we know in these projectile motion problems, that ax is equal to 0 meters per second squared. Okay, let's see, can I go down from here? Let's watch this clip, and this is a nice sort of typical projectile motion problem. It's probably about the easiest projectile motion problem that you'll have in this type of scenario. We'll work through several different types, but this is sort of the bare bones, the basic type of projectile motion problem. And in this problem, we're going to have an object that starts over here, travels, and then returns back to its same initial horizontal position. So it starts at y equals 0, goes up, comes back down again, and returns to y equals 0. Have you ever seen this flick with Nicolas Cage, Gone in 60 Seconds? In the movie, Nicolas Cage, he's like a car thief or something. His brother gets kidnapped. He's like a retired car thief. His brother gets kidnapped, and then this guy says, you have to steal 12 of these really famous cars in order to get away. You know what I'm talking about? Listen, don't be a car thief. That's certainly not a good idea. It's glorified in this movie, but I don't think it's good advice at all. Like, you probably go to jail. And what advice do I give to you? Have I given you this advice? Have I given you any advice before? Okay, the advice is don't go to jail. It's really bad to go to jail. Like, there are lots of other bad things you can do, but it's a bad idea to go to jail. Okay, anyway, so I'm saying, in the end of the movie, he's in this Shelby GT, a Mustang Shelby GT, and he comes up to a traffic jam. Oh, but fortunately they left the ramp up from the tow truck, and he goes and he hits the ramp and jumps over all the traffic and goes on his merry way and gets away from the cops. You know what I'm talking about, that scene? Sorry if it's a spoiler for you, but let's watch this. And as we watch it, we need two pieces of information in order to figure out both his range, his x range. So I want to know what is his x, and then also what is his maximum y. We can figure out both of those. I also want to know what is his speed at impact. What is v final equal to? Okay, I need two pieces of information. So as we're watching the clip, think about what are those two pieces of information, and then you can see them in the clip too. See if you can pick them out. Okay. So what are the two pieces of information that we need in order to find his range and his maximum height and his final speed? I need to know his initial velocity. Anybody catch that? It was about 100 miles an hour, right? Just before he hit the ramp, I think it showed a little under 100. So we'll just say 100 miles an hour. Let's go ahead and convert that into meters per second. We need two conversion factors. What are the conversion factors? What do I need to convert? Hours to seconds and miles. So we'll do miles first. Miles goes in the denominator or numerator. All right, so 1 mile is 1609 meters. And then 1 hour is how many seconds? 36, 60 times 60. All right, and that's equal to 45 meters per second. So he's going about 45 meters per second. And then something else I need to know in order to find his range. I need to know his angle. That's right. So what is his angle? Or what can we make? Can we make some assumption about his angle? What do you want to say? Right, why would we say 45? It gives us maximum range. So at 45 degrees, it gives us maximum time in the air as well as a maximum V0x. Or it maximizes both of those just right so that you get the maximum range. So we'll say that theta equals 45 degrees. Listen, a 45 degree incline, that's a big incline. So his angle probably wasn't 45 degrees, but we'll just assume that right now. All right, so the first thing that we need to do here is to find the time that he was in the air. And most of the time in your projectile motion problems, unless the time is provided, that's going to be your big task, is to find the time that he's in the air. We can do that a couple different ways, but it will almost always involve using the y motion. The y motion will dictate how long it's in the air. So we're going to use my notes here. Our first step, and almost always this is going to be our first step, is to find the time. All right? And to find the time, we're going to use the y motion. Easily. Cranky, pretty good at catching stuff. Who's good at catching stuff? All right, Emma. So look, I can throw this to Emma by 2D motion in a couple different ways. I'm going to throw it like that. I can throw it like that. I can throw it. Or I can throw it like this. Which requires more time? The first one. Can you throw it back to me? All right, so when I throw it up high, it requires a lot more time than when you throw it down low. So how high it goes in the air will tell you how long it's in the air. It's still in the same x direction, the same x distance, but how high it goes in the air will determine how long it's in the air. It determines your hang time, how long it hangs. That's why those guys that play basketball, they like to throw their free throw shots really up high because you get a lot of hang time. It looks a lot cooler. Yeah, it looks really cool. But the distance that you go up in the y direction determines the amount of time that it's in the air. So first we're going to find the time that it's in the air. We can do this a couple different ways. This is exactly the same problem as this, and finding the time that it's in the air. Y'all remember how we approached that problem? Yeah. How do we approach that problem? If I throw something up and then it comes back down again, how did we determine the amount of time it's in the air? Well, we used a little trick, right? Or some information that we knew, and that is that v in the y direction at the top is equal to 0, and so I say vy equals v0y plus ayt. And I'm going to call this top, vy top. And so that's going to be 0. v0y is going to be v0 times sine of theta. That's 45 meters per second times the sine of 45 degrees minus 10 meters per second squared. That's my acceleration in the x direction. It's actually a plus, a negative 10, times t. And then we solve this for t. And I find that t is equal to 3.3 seconds. Can I show you another way of doing this? Yes, I shall. Another way of doing this is, I know at this point that y is equal to 0. I also know at this point that y is equal to 0. So I can start with this, y is equal to v0y times t plus 1/2 ayt squared. And I want to know what is the time here. Now what should I get if I solve for this time? I should get 6.6 seconds, because I know up here it's 3.3 seconds. So I should get 6.6 seconds. Actually, let me double check this number. 45 sine of 45 divided by 10. Oh, I'm sorry, this is actually 3.2 seconds. So I should get 6.4 seconds over here. So what I'm going to do is I'm going to say 0 equals 45 sine of 45 times t minus 5 times t squared. Are you guys able to solve this? You remember how to solve this from algebra? Okay, you factor out a t. You say 0 equals t times 45 sine of 45 is 32 minus 5t. So notice this equation has two solutions. One of the solutions is what? Is 0. So one of the solutions is t equals 0. And then the other solution is take this part and set it equal to 0. So I have two solutions. I have, if this is equal to 0, this equation equals 0. The other is, what if this is equal to 0? And that would mean t is equal to negative 32 over negative 5. I get 6.4 seconds. So that means that at the end of the trajectory, y is equal to 0. But what is the physical meaning of this, at t equals 0? At the beginning of the trajectory, too, y is equal to 0. Sometimes you'll need to use this technique in order to solve for the time. And I'll show you some examples where you need to use the y position. Or sometimes you can use this technique, where you're using the y velocity at the top of the trajectory to find the time at the top of the trajectory. We'll see different problems where either might be appropriate. But for now, we know that the time at the top is 3.2. The time at the end is 6.4. And actually, if you watch the clip, it is about 6 or 7 seconds total that he's in the air. So it seems fairly legitimate. Okay, so we found our time. We've characterized our time. We found the time here, and we found the time here. But gosh, what are we looking for? Well, we're looking for the maximum height and the maximum range. So in order to do that, remember these equations that we use, these kinematics equations, they're just functions. They describe the x position as a function of time, or they describe the y position as a function of time. So if I want to know the x position at a particular time, and I know dx, and I know t, all I need to do is plug in that time, and I'll find that x position at that time. I just need to know the time, and then I can find the x position. So let's do that. Let's find this x range. I can say x is equal to 45 cosine of 45 times t. Oh gosh, which t do I use? I have two times. I have 3.2 and 6.4. Are you sure? Kind of sure. Yeah, you're right. It is use 6.4 because at 6.4 seconds, that's when he's over here. And that's what I want to know the x position of. So I say times 6.4 seconds. And that gives me 32 times 6.4, 200 meters. 205 meters. That's right, it's 200. That seems a little high, right? Like 200 meters, that's 2 football fields. But what was our initial assumption that could make this a lower value? The what? The angle theta. 45, let's say that's a big angle. I don't think that truck was at 45. It might have been more like 30 or 20. So this would be made smaller if our angle theta was smaller. Now, it's not just a matter of making this smaller. You have to go back, because when you make the angle theta smaller, it also makes the time smaller. So you have to go back and rework it. But we'll just take that. And then, if we want to know the y position, we say y is equal to 45 sine of 45. That's v naught y times t. Do I use 6.4 here? I use 3.2 because I want to know the y position at the top of the trajectory, and that y position is at a time of 3.2 seconds. By the way, if I wanted to know that, say, the y position over here, I don't know the time at that position, but if I did, I could find the y position. I just plug in that time. We'll see some problems where we have to do that, actually, where we have to find the y position at some other point that's not in the middle or not at the end. That's v naught y times t plus 1/2 ay times 3.2 seconds squared, 1/2 ayt squared. And this works out to be, I don't have it written down, 45, sine 45, this is 32, 3.2. Minus 51. Uh, 51, I guess. Is that right? 51 meters? Yeah. Okay, so 51 or 50 meters would correctly. Minus 51, well, because I had a negative here for my acceleration. I had a 1/2 times 5, that's 3.2. Be careful, a lot of people will miss points because they use a positive 10 for their acceleration. But whenever we're dealing with the acceleration due to gravity, it's always going to be a positive value. Until we get to next chapter and we're dealing with weight. But for now, it's always going to be positive. Okay? So that's it. That's our y position. It's a good basic kind of projectile motion problem. You could see one like it on the test. Likely, though, you'll see one with some slight kinks in it, but we'll work through some before we're done with this section. Y'all clear on this? Okay with this so far? Let me just step back through the procedure that we did. First thing we did was we just assessed what we knew. We knew the initial velocity and the angle. Then our next step is to find the time, and usually, almost always, we're going to use the y motion to determine the time. Almost always, we use the y motion. We had two different ways we could find the time. We could consider the velocity in the y direction at the top and figure out the time up here. Or we could consider the y motion, the y position, in which case we find the time at this position and at this position. Either way is fine. Either way is about the same amount of work. Yeah. Okay, let me finish going through this, and then we'll do that. It's easier than you think. And then we find the x range, which is just dx times t. This is our x component of our velocity. Hopefully you know how to do the x and y components second nature by now, but it's the cosine of 45 times the initial velocity. Then figure out which time that we're going to use. We use 6.4, and then that gives us our range. And then we do a similar thing with our y position at the maximum height, but using a different time. Now, Kyle. Yeah, so Kyle asked, what is our final velocity here? What is our final velocity here? If you think about it for a moment, you should be able to say right off the top of your head, what is the velocity here? We had a question actually on the test that where you throw something up and then it comes back down. Remember that question? We had it. It's what? It's going to be the exact same speed because we start out, think about our vectors, our Vy is in that direction, and then it gets smaller, and then it goes away, and then it increases, but in the negative direction. But these two vectors are exactly the same. They're just in opposite directions. And Vx, it doesn't change at all throughout the trajectory. So I have the same set of vectors here and here, except one of them split. So the speed is going to be the same. It's going to be, I think it's 45 meters per second. What is the direction of the velocity over here? Think about it. I've just flipped one of the vectors here. I know over here that the direction, what was the direction? We said it was 45 degrees over here. So what is going to be the direction over here? Well, just looking at the vectors, I know that it's going to lie in the fourth quadrant. Okay, but what is going to be the actual angle for the final velocity of these two vectors? I'm sorry, what? It's going to be negative 45. It'll be the same angle, but just flip in the opposite, the opposite quadrant. Okay, that's a good question. Thank you. All right. Y'all clear on this, folks? Lots of projectile motion problems in the homework, too. And we'll work through some more of the supplemental problems that you have in here at the end of your homework. Okay, let's try this. Soccer ball kicked at an angle of 30 degrees. If it requires 1 second to reach the goal, what is its initial velocity? This one's similar, but a little bit different because you have different information given, but you'll still use some of the same ideas. Here I'm looking for the initial velocity. Yeah, you want to push it? If I know that t equals 1 second right here, what is t up at the top? It's 0.5 seconds. I'm going to write that in. That might help you. I'm also going to write the equations over here. Be careful that some of you are solving for v naught y, and then you're reporting that as the answer. That's not what I'm looking for. I'm not looking for v naught y. I'm looking for v naught. So some of you have correctly given, I'm pretty sure this is what you did. You correctly solved for v naught y, either here or here, and you're reporting that answer. That's not what we're looking for. We're looking for the initial speed of the object, not the initial speed in the y direction. All right, we'll do about 10 or 15 more seconds. Remember, you can ask your neighbor, just ask your neighbor and see what they put. Check your answers. stop at 435. 435? Just guess if you don't know. Okay, good. That's good. A lot of you have put A, but D is previously because of what I had said. But let me show you how you do this. So D is the right answer. So, which of these equations could I use? First, second, and third. What did y'all use? Or you just guess? The second one, right. I can use the second one because I know everything in that but one piece of information. Because I know Vy, I know Ay, and I know T, at least when I'm looking at the top of the trajectory. I know that Vy is equal to 0, V0y, I don't know, but I can find it, plus Ay is negative 10, and T is 0.5. So V0y is equal to 5 meters per second, which many of you would put. You'd put A, but A is not right. Because V0y is equal to V0 times sine of theta. That's going to be V0 then is 5 divided by sine of 30. Sine of 30 is a half, so this is equal to 10 meters per second. And so that's the right answer. Okay? So this is a very similar problem, but you just have to take a different tack. The problems will only differ in the information that you have, but largely you're going to work them in the same way. It's just you'll approach them from different sides because of the information that you have. Let's look at this one. If you're in lab, this is like what you did in lab. Or if you're not in lab yet, you'll do it this week. You fire a projectile from a table in the X direction, as this figure shows. So this thing, it shoots out in that direction at 5 meters per second. It travels 1 meter, or excuse me, the Y displacement is 1 meter. How far does it travel in the X direction? We'll have a more complicated problem like this in the supplemental problems to the homework that we'll work in class. The first thing that you want to do in this problem is find the time. What motion do we consider almost always to find the time, the X or the Y? The what? The Y. Yeah, we'll consider the Y. So I have this thing, is dropping from 1 meter. If I drop something from 1 meter, you ask, how long does it take for that thing to fall 1 meter? So that's going to be your first task. You know everything you need to do to find that. And then once you find that time, you know the velocity it's traveling, so you can figure out the distance that it travels in that time. So 2 steps, you need to find the time for it to fall 1 meter, and then you need to find the distance that it travels in that time. Anybody have the time that it takes to fall 1 meter? Right, 0.45 seconds. That's the time. Okay. Guys, use this as good practice. This is a good place to practice for the exam. I'm going to help you out. I'm going to write down what we know here. I know that my AY is equal to -10. I know that my Y displacement is 1 meter. Wait, is it 1 meter? Or is it what? It's actually -1, because I'm starting up here at 0 and I go down to -1. I know that the velocity initial is 5 meters per second. And I know that the angle theta equals 0 degrees. Because the angle theta equals 0, I can further say that this V naught is equal to our V naught x. Because the cosine of theta is 1, the sine of theta is 0. But you would have found that when you find the x and y components. Alright, we'll do about 15 more seconds. And compare your answers if you like. I've already said that the t is 0.45 seconds. I'll show you how to get that. I'm going to stop at 5:10. 5:10. Okay, good. Let's see. I'm pretty sure that's right. That B is right. So first I find my y. I say y is v naught y times t plus 1/2 at squared. Ay. This is easy because v naught y is 0. So I get rid of this whole term. That means I don't have to use the quadratic to solve this. Y is -1 because, as we said, it starts at 0 and it goes down. 1/2 of a is -5. Half of -10 is -5 times t squared. My negatives go away, so t is the square root of 1/5, and that's equal to 0.445, or I'll call it 0.45 seconds. Then I want to know x is going to be vx times t. Because the angle is 0 degrees, v naught is equal to v naught x, and the acceleration in the x direction is 0, so v naught x is vx. So this is going to be 5 meters per second times 0.45 seconds, and that's equal to 2.3 meters. So B is the right answer. You could have a problem like that, and again, we'll work some in the supplemental section that's very, very similar to this, but just with some added complications. So the details, it's the complications that make them difficult, but we'll work through some of those to give you some practice. Lots of these in the homework too. There's lots of projectile motion problems. Let's see, I think 82%. That's worth a joke, right? Is that worth a joke at 7:30? Huh? Could never run out. Hundreds of jokes. Let's see. The police, they came to my house the other day. They knocked on the door. They said, "Mr. Young." I said, "Yes." "Can we have a quick word with you?" I said, "Okay." Velocity. Because that's a quick word. You get it? They weren't too pleased. All right. Let's come back to this. Let's do this other quick test. Large cannon is fired over ground level, over level ground at an angle of 60 degrees above the horizontal. What is the maximum height? It gives you the muzzle speed. This is exactly like the Nicolas Cage problem, except it just has different numbers. So exactly like that. I want to know the maximum height. I want to know what is y. First step will be to find the time by one of those methods. The second step will be to find the y displacement at the top of the trajectory. Just going to write a few things up here. Find the time, and then once you find the time, you can find the y displacement at the top of the trajectory. Remember, to find the time at the top, you're going to use the information that we have that's not stated, which is that the velocity in the y direction at the top is equal to 0. And with that, you can determine the time at the top of the trajectory. Once you get the time at the top, it's fairly straightforward to figure out what is the y position at that time. Don't forget, too, that you'll need to figure out your y component or your x component of your initial velocity. Y component is v naught sine theta. X component is v naught cosine theta. Feel free to ask your neighbors. Your okay. So our first step is to find the time. As I said, to find the time, we have two ways with the extreme gauge problem. I would either look at the y position, or we could look at the velocity. Let's use this technique. So I know that at the top of the trajectory, that Vy is equal to what? Is equal to 0. What is V naught y? Has anybody found that yet? It's 87, right? It's going to be 100 times the sine of 60. Sine of 60 is 0.87, so this is going to be 87. And I know what AY is, negative 10. So I can solve for t at the top of the trajectory. Once I solve for t at the top of the trajectory, oh, it is what it is. This is 0, this is 87, solve for t. Once I find that, how can I find the y displacement? First, second, or third of these. The second of these, that's the only one that gives you y displacement. And in this, once I find the time, I know everything there. So it's basically just plugging in the correct number. Can I get y'all started a little bit? All right. It's going to go about 15 or 20 more seconds. I'll stop at 6:10. 6:10. If you're not certain, just guess. We're going to stop at 6:10. Okay, I think A is right. I'm going to go ahead and mark it correct. So to find the time, as I said, we're going to use this to find the time. I say 0 equals 87. V naught y is 100 sine of 60. That's equal to 87 meters per second. Minus 10, because AY is 10, times T, which I want to know. And then I find T then is negative 87 over negative 10, or 8.7 seconds. That's a long hang time, almost 10 seconds, but it's going really fast. It's going at 100 meters per second, so it's going to go up to a very high height. All right, and then I use this to find my y. I say y is equal to v naught y, which is 87, times t, which is 8.7, minus 5, that's half of negative 10, times 8.7 squared. Is this 400? Okay, and that's equal to 400 meters. That thing goes up to 400 meters, 4 football fields high, and a hang time of 9 seconds. All right, so this is how you work this problem. And so we're going to work through a bunch more problems. So if you're not getting this, that's okay. We'll have another day on projectile motion. Let's see what's next. Let's go back to this. What do you do when the time is not given? I sort of covered this a little bit, but usually what you're going to do is you're going to analyze the y motion. Almost always this is what you're going to do. So we'll analyze the y motion. Like, for example, we're going to pick some information that we'll have. So, for example, we know that v at the top in the y direction is equal to 0, like we've been doing. And then from that information, you can figure out the time at the top. And then if it's symmetrical, that is, it begins and ends here and here, then you can double that time to get the total hang time, just like we've been doing. We'll also see another problem in the supplemental problems where we cut it short, so it lands somewhere right here, and we know the y displacement. You can do a similar thing here, where if you know the y position at that point, then you can find the time at that point. Now that doesn't tell us a whole lot about times at other points, because if we find the time at this point, we can't extrapolate and find the total time, because, you know, it's not like here where we could just double it. You can't do that here. We'll work through a problem like this next time, where we cut it short. It doesn't go all the way down. It stops somewhere. Another way is to analyze the x motion. This doesn't come up real often, but sometimes it does. Where if you have a trajectory and you're given some information, you're given both x and you're given vx, then you can find the time. So if you're given the x displacement and the velocity in the x direction, then you can find the time. Let's see, x is equal to vx times t, so t is x over vx. That's less common in projectile motion problems, but we'll see a problem where you have to do this in order to find the time, where it gives you the x displacement and the velocity of the x direction. So those are going to be sort of your two tacks approaching these problems when the time is not given. When the time is not given, sort of be ready to sink in and get into all the details. Because if the time's given, the problem is usually pretty simple. But if the time's not given, you're going to have to use one of these techniques, either analyzing the y or the x motion, depending upon what's given. Okay, let me hand back your exams. And again, the solutions are online, so you can find the solutions there. If you have questions about why I counted off, just please let me know. And once you get your exam, you can go.